Okay, good morning, everybody. This is the last section of chapter 19 that I am going to talk about today with you. Um, so, this will be our last lecture video related to our course, um, and it will cover the remaining parts of chapter 19, the last chapter that we will be covering. So basically, after this lecture video, we will not have any more videos. Okay, so this is the last lecture basically. All right, with that being said, let's take a look at the section 19.3, the equilibria of a slightly soluble ionic compound. Um, Now, ionic compounds by definition are made of a metal and a nonmetal. So ionic compounds have limited solubility. Now, for a slightly soluble ionic compound, usually we have equilibrium established between the solid solute and the aqueous ions that are produced due to the dissociation of that solid or ionic compound. For example, for a solution of PbF2, which is an ionic compound, and it's a slightly soluble ionic compound, we have the ions Pb2 plus and F minus produced according to this equilibrium reaction. Now, as for any equilibrium system, we can immediately write down the equilibrium constant, which is the concentration of the product divided by the concentration of the reactant, as we have discussed in the previous chapter. Now, when it comes to the equilibrium of slightly soluble ionic compounds, since we have a pure solid on the left-hand side, which is in this case PbF2, and we know that from the discussion in previous cases that the concentration of a pure solid or a pure liquid does not contribute significantly to the equilibrium expression. So therefore, we are just simply ignoring the concentration of PbF2 in this expression. So therefore, if you look at the next lecture slide, I had a hard time trying to get that one out. Okay, so you can see, let me just kind of organize this page here a little bit. Okay, you can see that the KSP can be basically written as Pb2 plus and F minus squared without the inclusion of PbF2, which is the pure solid and is the solute. Now, the KSP is called the solubility product constant. SP stands for solubility product, and the K is, of course, the equilibrium constant. So it's solubility product constant. And since it's usually written in terms of the ions in the expression, and we do not include the concentration of the pure solid, therefore, what we see appearing in the KSP is just product of ions. We also call it the ion product constant. Okay, so the KSP has basically two names: solubility product constant or the ion product constant. Now, sample problem 19.5 on page 865 in your textbook takes you through some useful practices on how to write KSP for different ionic compounds. For example, magnesium carbonate and silver sulfate. There are some examples here. For example, for MgCO3, we can write the expression as Mg2 plus and CO3 2 minus for the dissociation of the ionic compound, and the KSP becomes basically the product of these two ions without MgCO3. And also for Ag2S, we have 2 moles of Ag plus and 1 mole of S2 minus, and the KSP is Ag plus squared. Always remember to include the coefficient in the expression of KSP, and also S2 minus. Okay, so the concentration of MgCO3 and Ag2S are not included in that expression, as you can see. Okay, so now we go to the next slide. This is sample problem 19.6 on how to use the solubility information to determine or to calculate KSP. Okay, so if you know the solubility of a slightly soluble ionic compound, how do we determine the KSP from that information? Okay, now I have also included the definition of solubility. That solubility, we are using symbol S for solubility. This is not to be confused with the state, the solid state, but it's actually rather referring to the solubility. So solubility, or S, of a solute is defined as the maximum amount of that solute that can be dissolved in a fixed quantity of a given solvent or solution, okay, at a given temperature. The solubility is temperature dependent. For example, the solubility of sodium chloride is 39.12 grams per 100 milliliter of water. So that basically, that means that at 100 degrees Celsius, the maximum amount of sodium chloride that can be dissolved in 100 milliliters of water is 39.12 grams. Okay, so again, it's the maximum amount of the solute that can be dissolved in a given quantity of solvent or solution. That we refer to it as the solubility of that solute. Okay, now, so this is just an example of what a solubility is. Now, this problem is giving us the solubility of lead sulfate, or PbSO4. So this is the solubility of lead sulfate given to us in the problem. According to this problem, the solubility is 4.25 times 10 negative 3 gram per 100 milliliter of solution. So in other words, the maximum amount of lead sulfate that can be dissolved in 100 milliliter of an aqueous solution is 4.25 times 10 negative 3 grams. Okay, and the question is, what is the KSP based on this solubility data? What is the KSP for lead sulfate? If we want to calculate the KSP, all we need to know or all we need to have is basically the concentrations of the ions produced due to the equilibrium that exists between the solid and the aqueous components. Okay, so first we write the dissociation reaction or the solubility equilibrium reaction, I should say, for the lead sulfate. So lead sulfate is the solid. It's at equilibrium with its component ions, Pb2 plus SO4 2 minus in the aqueous phase. Remember, these are all in the aqueous phase. Always, this is in the solid phase, right? Okay, so the KSP is going to be the product of Pb2 plus SO4 2 minus, but they are in molar concentrations. Remember that the bracket stands for what? Concentrations in units of molarity, or moles per liter. So we really refer to these concentration now in the context of solubility, we call them molar solubility. Okay, molar solubility. Now, what we have is the grams of PbSO4 per 100 milliliters of solution. Okay, in the next slide, you'll see that we can actually convert the gram per milliliter of solution to moles per liter, or in other words, to molar solubilities. Okay, so I'm basically explaining at the top of the page that from the mole ratio of the reaction, we can see that for 1 mole of PbSO4, we get 1 mole of Pb2 plus, we get 1 mole of SO4 2 minus. So therefore, the stoichiometry tells us that the mole, or in other words, stoichiometry is another fancy name for mole ratio. The mole ratio tells us that the concentration of all these three components are the same because they take place in the same mole ratio. Okay, 1 to 1 to 1. Now, why do we have to worry about the mole ratio here? Because remember, the KSP is going to be the product of these two ions, right? So if we know the product, the concentration of these ions, then we can calculate KSP. So where do we get the concentration of these two ions? From here, okay? Because this is the information given to us in the problem. So we need to convert that to be the molar concentration so that we can use it for the KSP. So the concentration of PbSO4 can be determined from the information given to us in terms of grams per 100 milliliter of solution. So basically what I've done here, I've described to you that we need to convert the gram per 100 milliliter of solution into moles per liter. Okay, so this moles per liter is also known as the molar solubility. Okay, so what I'm going to do now is basically convert this number to this unit, basically moles per liter. So from grams per 100 milliliter of solution, I'm going to convert to moles per liter of solution using this algebraic step. So the conversion, the first conversion, okay, so this number is the same number as that, right? So the first thing I want to do is I want to convert from milliliter to liter. So I want to have liter at the bottom and milliliters on top, right? So that the milliliters can cancel each other out. So 1 liter is 1,000 milliliter. We already know the conversion between liter and milliliter. Okay, so the first step is basically the conversion of liter to milliliter to liter, right? Now the second step, I want to convert this grams to moles. So I have to have moles on top, grams at the bottom, right? And this number, 1 mole of lead sulfate is 303.3. Now that is the molar mass of lead sulfate. That is what we find from periodic table, okay? So I'm dividing the gram by the molar mass to get the number of moles, basically. So basically the grams cancel each other out and we get moles. So only unit remaining is moles and liter. So this, when you go through this calculation, you get 1.4 times the -4, which is moles per liter, or just simply molarity, right? So therefore, this is the number that we refer to as the molar solubility. So if the molar solubility is given, if the solubility is given in grams per milliliter, we need to convert it to moles per liter of solution, or in other words, to molar solubility. Okay, so the molar solubility is 1.4 times the -4 m. And now, for the next slide, we are going to use this information. We are going to use this information to convert the to calculate KSP, basically. So we already know that mole ratio exists, right? And we already know that the concentration or the molar solubility of lead sulfate is 1.4 times the -4. So therefore, the KSP is going to be the product of those two ions, and we already have them. and when you multiply those two numbers, you get that. Okay, so the KSP can be easily determined. But first, we must convert the gram per 100 milliliter to moles per liter in order to get the KSP. Okay, so the next sample problem is actually a more important sample problem because it basically tells us how to calculate the solubility, which is frequently needed from the KSP data. So in other words, if we have the KSP for a given ionic compound, how do we find its solubility? Okay, so how do we calculate the molar solubility of calcium hydroxide, which is CaOH2 solid, in water, given that the KSP for that is 6.5 times 10 negative 6. So we have the KSP now. We don't have to calculate it. And from that, now we want to go back to find the solubility. So this is basically the reverse of what we did in the previous problem. Now, anytime, and this is very important, anytime that we need to calculate solubility, or S, given KSP, we need to set up the equilibrium or the ice table. Remember, still we have solubility as an equilibrium process that exists between the solid component and the aqueous component. Okay, so there is equilibrium that is taking place between those. And we need to set up the ice table to find the solubility. How do we do that? The next slide is going to walk us through it. Okay, so here we have the reaction of calcium hydroxide going to Ca2 plus and 2 moles of OH minus. We set up the ICE table, the ice table. Now, note that I have not indicated any data for calcium hydroxide because the concentration of calcium hydroxide solid is considered to be constant. It doesn't change that much during the course of the reaction. It's pretty much like H2O or water that we ignored during the setup of the ice table in the equilibrium chapter. Okay, so we start with the I. Initially we have nothing present, and then the change we're going to call it S for calcium 2 plus and 2S for OH minus. Okay, now the 2 is basically because of that 2 moles of OH minus. Okay, so this S stands for solubility, which is change, and it's always a positive number for product. Okay, so this is positive S, this is positive 2S. And then E, as you know, is I plus C, so 0 plus S gives you S, and then you have 2S. So we have seen this before. This is nothing new to us. But instead of X, we are using S for solubility to distinguish it from the previous concepts of equilibrium, where we had aqueous components on both sides of the reaction. Now, the KSP is the product of calcium 2 plus and OH minus squared in molar concentrations. And now, well, the KSP is 6.5 times 10 negative 6. Calcium is S. OH minus is 2S squared. Make sure you remember that this 2S has to be squared at the end, okay? Because that, so in other words, this 2 appears twice, one here, one time here. So make sure you don't forget that. So the 2S squared is 4S squared, so times this becomes 4S cubed, okay? So now, and also I've indicated one more time that the contribution of calcium hydroxide solid is constant and is not included. Now, so we're going to solve for S. S is what we're looking for, the solubility, right? So basically, S is going to be the cube root of this ratio. So in other words, we take the 6.5 times the negative 6 divided by 4. That will give us s cube, but s is the cube root of that. Okay, we have to take the cube root of that ratio. And that's why I have this square root with the 3 written there. That is the sign for the cube root. So s is 1.2 times the negative 2. Now, I've also, in the next slide, I've indicated that 6.5 times the negative 4 is 1.625 times the negative 6. And then once we get that, then we use on my calculator, which is I'm using my calculator on my phone. We have a function on this is on iPhone actually. There's a function, the cube root of x. Okay, so once you get this number, press this function here, and then that will give you 1.17 times the negative 2, which is rounded off to 1.2 times the negative 2. Okay, so taking the cube root, basically using that function to take the cube root. Okay, now, so this problem explained to us or showed us how to calculate the solubility in water with no common ion being present. Now, the question now becomes, what happens if we take the same compound, but instead of water, place it in an environment where there is a common ion present? For example, okay, so in sample, so let me just go back and read the information one more time. So the question is, so in sample problem 19.7, we calculated the solubility of calcium hydroxide in water with no common ion. Now we want to calculate the solubility of the same thing, calcium hydroxide, in 0.1 molar calcium nitrate as opposed to water. So now this is our solvent. Now this solvent has an ion in common with our compound, and that is calcium, as you can see. Okay, with calcium 2 plus being the common ion. Okay. Now, the KSP for calcium hydroxide is still 6.5 times the negative 6. That's given to us. Now, the question is, so let's say instead of water, I put this calcium hydroxide in 0.1 molar calcium nitrate. Now, what is the solubility? Okay? So again, okay. Sometimes it's kind of hard to get these papers separated. Okay. So now this is showing us how to calculate the solubility of calcium hydroxide in 0.1 molar calcium nitrate. So now we have a common ion present. Okay. So again, we set up the equilibrium ice table, but in the previous case, the initial amount of Ca2 plus was 0 molar. Here is 0.1 molar, and that comes from 0.1 molar calcium nitrate being present as the solvent. Okay? So remember, the common ion, for the common ion effect, we usually have, when we calculate solubility in the presence of a common ion, we usually have some already existing initial amount for one of the ions on the right-hand side. In this case, it happens to be calcium, which is 0.1. Okay, so nothing for OH minus. The change is S here, 2S here, like previous case. And now it's 0.1 plus S, 0 plus 2S gives you 2S. Okay, so we set up the KSP again, Ca2 plus times OH minus is squared. So this is 0.1 plus S times 2S squared. Now, if we don't make any assumptions here, then we have to use the quadratic formula to solve for S. But again, as I have explained before, we usually make some assumptions to avoid using quadratic formula because it's much easier to actually make the assumption and then check it rather than to go through the quadratic formula and solve S with the quadratic formula. So the assumption here is that since K is small, this is the KSP is small, we can assume that the solubility is also going to be small. And as a matter of fact, we are going to assume that solubility is smaller than 0.1. Okay, so all assumptions, we are going to make the solubility small compared to the initial concentration of the common ion. Okay, so if S is much smaller than 0.1, then 0.1 plus S becomes almost equal to. This sign is used for almost equal. So 0.1 plus S is almost equal to 0.1. So this becomes 0.1 times 2s squared. So I've gone through the algebra here. That's 0.4 s squared, and s is the square root of that, which is 4 times 10 negative 3. And now one more important fact that you should notice about this problem is that that the solubility here is much smaller than 0.1, and therefore that assumption is justified. Okay, that assumption is justified. Now, I have seen in the textbook that they are using the 5% rule to validate the assumption, and you can also do that. In other words, if you divide this number by the initial concentration, which is 0.1, and times 100%, it should be less than 5%. But we don't need to do that at this point because we can see that actually S is much smaller than 0.1. Okay, now that is basically all we wanted to talk about. The concept of solubility, basically, how to write KSP, and you can also find some similar problems at the end of each sample problem that I've gone through here to get more exercise or practice related to these concepts. Now, as I have indicated in the beginning of the lecture, this is our last lecture, and there will be no more lecture videos posted. Next Tuesday is the last day of classes. Of course, you know that on Tuesdays we don't have classes. So therefore, this is going to be our last lecture video. And now Wednesday is, so I have written down these important dates here. So let's go through them one more time, just in case you were not here on Thursday. So, so the important dates is that Tuesday is the last day of classes, all classes, not just Chem 108. Last day of classes. Of course, we don't have a class on Tuesday. Wednesday, the 13th, May 13, is the last day to submit all Connect homework problems. And remember, there is no more extension to be given after that date. So it's absolutely important to submit all of them. Thursday, May 14, is the final exam for section 003. It starts at 1 o'clock, ends at 3 p.m., so 2 hours. And Tuesday, May 19th, is the final exam for sections 1 and 2. Again, the same time format from 1 to 3 p.m. Please make sure to check your Bowie State email frequently to stay informed and connected regarding any changes or any information or any updates related to the final exam coming up. Good luck and stay safe. Have a great day. Bye.